Hi, Chris Kuzmal here. We're going to talk about the fundamentals of a binary tree. A binary tree is like a linked list, but we replace the notion of a previous element with a parent node. The notion of a next element is replaced with the notion of a left child, and we add a notion of a right child. Let's look at what we mean by this more precisely. A linked list has a head. A binary tree has a root at the beginning. The next element for the head of a linked list is pointed to from the head. The root points to its left child, and we could have chosen to have the right child be in the role of being the next element, but we chose the left child. So the left child is pointed to from the root. The thing that's pointed to from the head of a linked list is called an element. The thing that's pointed to from the root is called a node, and the root is also considered to be a node, just as the head is considered to be an element in a linked list. The root is considered to be a node in a binary tree. The previous element of an element is pointed to, and so the next element from the head, its previous element is the head itself. The left child of the root, that element, its parent is the root. So the role of previous is replaced with the role of parent. This is why the code is so easily transferred. Now then, the next and previous relationship between successive elements continues for subsequent elements of a linked list. For a binary tree, the root itself has a second, hence the bi in binary, a second node that is pointed to. The right child of the root is pointed to by the root, and that the parent of that right child is also the root. And each subsequent node in a binary tree might have a left or right child with a parent. And so the node that's a left child or the right child of the root appears here at the bottom. A binary search tree also has a binary search tree property, which says the value of the keys to the left of a node are all less than or equal to the value of the keys to the right of the node. So if we look over here, 3 to the left, we get a 1, 1 to the, and everything over here, everything to the left, this one, and this 2, they're all smaller than the 3, and every element over here is larger than or equal to the 3 that's at the root. And the property is more obviously met by elements below there. But this 2, you might think it's okay to make this 2 into a 3 since it's going to be bigger than this 1. That'd be okay. But if we make it into a 4, it's bigger than the 1, but it's then also bigger than the 3, which it is technically to the left of. So you can't make this 2 into a 4, even though if you just look at its parent, it seems like that would be allowed. And so that introduces one of the complications in preserving the binary heap, the binary search tree property. So now we're going to go on to see how to design test code for a binary search tree which obeys the binary search tree property.